Okay, so we're going to start with some notation that's going to help us talk about systems of equations and what their solutions look like. So this is the predator-prey system that we were working with last class. The prey grows exponentially in the absence of the predator, and interaction with the predator hurts it. And the predator decays exponentially in the absence of the prey, and interaction between predator and prey helps it. So we're going to use a vector notation to express this system. So if you took linear algebra, this is going to be familiar. Or multivariable calculus, you might have used some vector notation also. So remember, or know for the first time, that vectors are expressed with a bold print letter or a letter with a little arrow above it. So your book uses the bold print, so I'm going to follow that convention so that your notes will match the book. So we're going to let capital P of t, that's in bold, that P, it's going to be the vector R of t, F of t. So this is the solution vector, R of t, F of t. And you can also write a vector horizontally, kind of like a point, right? R of t comma F of t, if you want to save paper. But they mean the exact same thing. So this means that we have this other vector. If P is the vector R of t, F of t, then P prime is the vector R prime of t, F prime of t. And then we put our two expressions for R prime and F prime in a vector. Okay, so the nice thing about writing this as a vector is that the right-hand side of the equation, this guy, is a function of R and F. So for each R and F, we can plug in, and we will get a vector for every point in the RF plane. So R comma F is a point in the RF plane, and the vector is a direction. It's like a little arrow pointing you where to go. And since this vector that we're calculating is P prime, the derivative of P, those vectors are tangent to the solution curve that's traced out by R comma F. Okay. So if we plot a bunch of these vectors in the RF plane, we'll create what's called a vector field. So this is very similar to making slope fields, except that now we have three variables: time, predator, and prey, and we're just drawing the picture without time. Okay, so we're just doing a predator, prey, and at each RF, we're drawing a little arrow. So we could do a couple by hand just to see what the idea is. So let's say I want to calculate P prime. Right, P is a vector. It's hard to do bold when you're writing on the board, so I'll use the arrow notation. So P prime evaluated at 0, 0, right? That's an R comma F. That would be 2R minus 1.2 RF is 0, and negative F plus 0.9 RF is 0. So I have the vector 0, 0, which is just a dot. Arrow doesn't go anywhere. So at 0, 0, I've just got a dot. Okay. So let's try calculating the derivative vector at 1, 1. Plug in 1 for R and 1 for F. And I get 2 minus 1.2, which is 0.8. And negative 1 plus 0.9, which is negative 0.1. Okay, and then you plot that vector by going right 0.8 and down 0.1. That's an R and an F direction. So at 1, 1, I'm going to draw a little arrow that goes right 0.8, down 0.1. There's my vector. And then I could do a whole bunch of these, right? I could do P prime at maybe 1, 0. So I know when I plug in 1, I get 0.8. No, I don't. No, I don't. Sorry. because I got to plug in a 0. So if I plug in 1 for R and 0 for F, I get 2. And 1 for R and 0 for F, I get 0. So at the point 1, 0, I draw the vector 2, 0. So at the point 1, 0 right here, I'm going to draw a vector that goes right 2 and down 0. So it looks like this. This is going to get tedious, right? We could do this a lot of times, and we're just going to get a whole bunch of arrows. Eventually, it will give us a flavor of what the solution curves are doing, because these are tangents to the solution curves. But this is the kind of job that a computer is really good at and is really annoying for us. So a T89 can do it. You can look in your manual for how to do it. And there's also this free software. This is what I use whenever I'm making vector fields or sketching solutions to ODEs, and numerical solutions. So it's free, it's really cool, and it can do all kinds of other stuff besides ODEs. So you can go to that site and download it. And it's called WinPlot. And I think I actually planned to show it to you a little later in the class, so I'm going to open this up. Oh. Maybe I don't have it downloaded on this computer. All right, we'll download it later and I'll show you how to use it. So here's several vectors, okay, plotting a whole bunch of them. You're kind of getting a like circling motion, but it's still not super clear what's happening with the solutions, other than there's a little bit of a circling motion happening. So the arrows tell us the direction the solution curves are traveling in, and the length of the arrow tells us how fast the solution curve is being drawn. So picture it as like you're driving a car in a giant parking lot, and the parking lot has arrows all over it, and you have to trace out a solution curve by following the direction of the arrows. And when the arrows are long, you are driving faster, and when the arrows are short, you're driving slower, and you're tracing out the solution curve. Exactly. That's how we account for time, is the speed at which you draw the solutions. So often, in fact, almost all the time, having the arrows be all different sizes can really clutter the picture. So imagine, because they'll start to overlap, because you have them that'll be really long and they'll cross each other. And if you're trying to follow the directions and driving the car in the parking lot, you're going to be like, which way do I go, right? So we usually just take all the vectors and scale them to a small uniform size so we can see just the direction. We lose information about the speed, but usually we're okay with that because it makes the picture so much easier to read. So the result is called a direction field instead of a vector field because it just has directions and not lengths. So here's a direction field that I plotted for the predator-prey model, this one on the left. So this is the one that we started to do by hand, and we drew 3 vectors and gave up because it took too long. Right? So a computer can do it really fast, and now we have a really good sense of the circular motion, and it seems possible to plot specific solution curves corresponding to particular initial values. And remember that when you plot several solution curves along with equilibrium points, this thing is called a phase portrait. So I've done several here. So sometimes sometimes the vector field or the direction field can suggest where the equilibrium points are. Like here, it kind of like something is happening right there, right? We're getting closing in on that point. That's probably an equilibrium point. And the same thing, something crazy is happening at the origin because the slopes are going like this and like this and like this and like this. So like there's something special happening right at the origin, probably an equilibrium point. So it can suggest where equilibrium points are, and then we can find them analytically by setting each differential equation to 0 and solving that system of equations. So for this particular example, we found both of those equilibrium points last class. Okay, so let's take a few minutes to explore the software. So if you want to use it, you will know how. And then this one was negative y plus 0.9 xy. And then I want vectors. And I just hit OK. And I get a vector field. And then the very cool thing is that you can trace trajectories. So rather than having to like eyeball it, you go to, this is another thing that's not intuitive, you go to 1. Sorry, maybe it's 2. Why isn't it there? Oh man, I was just doing this last night. Yes. Where does it say initial value problems? Oh. Yep, okay, so sorry, this must be a newer version and he changed the name of the menu. Okay, so we want the dx dt trajectory. You open that up for IVPS and you give it an initial value like 1.5 and click draw and it draws your solution. So it's basically using Euler's method to draw that solution. We will learn how to do that in 2 dimensions later. So it uses a numerical method like Euler's to graph the solution. So this is really handy. So there's just 2 things you got to remember where they are for now. Go to equation, differential, dx dt, and then to get a solution curve, you go to 1, initial value problems, dx dt trajectory. I don't know. You should. So that is wind plot, and it's pretty cool. Another thing, I did find something in GeoGebra. It's not quite as good, but I'll show it to you anyway. I'll post this file because there isn't a inherent command in GeoGebra. Somebody had to write a little program to do it. So I'll post the file. It's called vector field, and it's coming. So in this one, you actually get vectors of different lengths. The limitation here is that your x-min and y-min and x-max and y-max can only go like, I think, -5 to 5. So you can only look at a certain window. But it can do cool stuff. So all you do is type in the equations here. You could do 1, 0, whatever. So I'll post that file too. You can use it if you want when you're doing your homework. Both free things. Okay. Your textbook also comes with software, but I was having trouble accessing it. So I had to find something else. But if you can access your book software, feel free to use it. All right, so here's a little note. Now that we're working with systems that have two dependent variables, we can kind of see, like in retrospect, why we've been using t as the independent variable all semester. Because now that our independent variables, we have two of them, now we can call them x and y and let t be the independent variable. And when you plot solution curves, they're now in the xy plane. So that's small reason why we used t all semester, so that we wouldn't ever confuse whether x is independent or dependent. All right, so I'm going to have you work through some stuff in your groups, and I will come around and help if you need it.